Hello. Hello and welcome to this video. In this video, we will look at inheritance and virtual functions, which form the basis of polymorphism, one of the pillars of object-oriented programming. Know that there are three pillars: polymorphism, inheritance, and encapsulation. As I said in my earlier videos, abstraction is not the pillar of polymorphism because abstraction is there in every language. Without abstraction, you cannot do programming. So these three pillars are commonly known as PI, P for polymorphism, I for inheritance, and E for encapsulation. Now, what do you mean by polymorphism? By polymorphism, we mean that an object taking multiple forms. Poly means multiple and morph means basically to change form into something else. So in C++ or in Java, a base class object takes the form of the child class object. How that happens, we will see very quickly. We will talk about vtables and vptr and all that, and how the compiler implements virtual functions. So if you have not watched my previous videos, you should go ahead and watch them. In the last video, we talked about inheritance and how different inheritance modifiers work. So without further ado, let's dive straight into the video. So we have a class animal. It has a public function speak, which says animal speaks. Then we have a class dog. We inherit publicly from animal, and it has the same function void speak and says dog barks. Now if we create an animal object A, like with new dog, and we say speak, then what should it print? Should it print the animals speak or should it print dog speak? Well, it is called static binding and it will print animal speaks. Okay, because we will see why, because in a bit, in one moment we will see this. Okay, so what happens when you take inheritance is that the object of dog will contain an entire object of animal. We'll see how in a moment. Later on we will see how it contains an entire object of animal into this. When it contains the entire object, it also contains the private parts. That is the surprising thing. Although dog will never be able to access animal, but it will contain the private parts as well. You will see that once we finish this polymorphism thing. Now, if you try to run this, let me recall my compilation command. Okay, we compile this and we run this. Okay, and it says animal speaks. So by that we can see that even though this object is of dog, pointer is basically pointer, is pointing to an object, but the real thing is the dog object. So if the dog object did not contain this, it wouldn't have written animal speaks. So certainly the dog object contains the animal object when the object is made. Now we look at a different program where the only change is this virtual world. Okay. Now when we create the dog object here and point to it by using an animal pointer, and we say A speak, it will print dog barks. We'll see how. So there you go. So what happened here? Now when we say virtual, the dog object will look at something, okay, inside the object, and it will go and look at dog speak. That is, it really cares about the actual object. In the last program, it did not care about the actual object, it cares about the type. This time it checks the actual object and invokes that object speak. So how does this work? So this mechanism is called a vtable mechanism. Note that vtables are not dictated by standards. The C++ specification never talks about how virtual functions should be implemented. They don't dictate the actual how of what the compiler should do. In practice, I think all compilers make use of vtable. So the vtable of animal will have two functions. For example, speak and eat, and dog has two functions. Now, what happens is when you have a virtual function, compiler embeds a vptr to this object. So suppose we have an animal object P and it points to the dog object, and dog object will have vptr. It will contain the dog object. Okay. No. This won't contain the dog object. This is animal. Okay. And these two are data members. All right. So vptr of animal object, or no, I'm wrong here. This is dog object. So animal pointer P will point to the dog object. Dog object will have vptr, and this vptr will point to the dog's vtable, which will contain only virtual functions. Okay, so that's how vtable is implemented. Now, to confirm that, let us write a bit of code that vptr is there. So suppose we will talk about something else also. Suppose we create an empty object. We will take a bit of wrong file name. We save this as, we call this class object. I have saved again. Okay. So now suppose we create an object of this class animal, okay, or we rather talk of, we say cout size of animal. Okay, let's see how big this animal object is. All right, that's not animal, class object. Animal this is class file animal. So we run this and it gives us output 1. Now the question is, why does animal class has a size of 1 when it has nothing? The reason is that the size is 1 so that when you have an object of it, though it should be able to uniquely identify. That is the main reason. When the objects will be made, it should have a unique address. That is why the size is 1. Now let's create a function, void func. Okay, let's give it a body as well. All right, so we have this function and then we have the body. Now let's look at the size of animal. Oops, I have not declared this virtual. Let me make it virtual and we'll see. Now the size is 8. So what happened? That 1 byte which was used to mark the object is no longer needed. Now we have a vptr which will be created along with the object, and that should be able to uniquely identify the object. But why the 8 byte size is there? So this is a 64-bit machine. Size of pointer is 8 bytes, and that is why the class object will now take 8 bytes, because the compiler is internally creating a vtable. All right. So that is how we see that this class is basically taking object. Now one more thing here. Let's give it an object and we just give an int a. So now it should be 12 bytes, right? Because int is okay. So why the int object did not come in picture? Because the class is not instantiated. Sorry, I'm in the wrong file. My bad. Int should have size of as well. It should be 12 bytes. I was correct earlier. So now we have 16 because somehow this int is now 8 bytes. Okay, I don't know why this is 16. It should have been 12. Okay, I got it. So here the structure alignment is coming in picture. Okay, so this int is becoming 8 bytes. For example, if you put another char C, it should not char C. Let's put it shortened S. Okay, let's see how much this is. So still it is 16. What should I put in here so that the size again explodes? Okay, so let me do a char C and int a b. Okay, and we'll see how big this is. What I'm trying to make a point is that how alignment comes into. Now it is 24 bytes. So you see what is happening here. Int is a 4-byte thing. Our VPTR is 8 byte. But when you do the word alignment, if you have a single int, that should also end up taking 8 bytes for the word alignment. Okay. Then you put a char C. Char C can go anywhere, but when you put it with another int, okay, if you remove this char C, it would be 16 again. 16. So 4 for int A, 4 for B. Or if there is a single int, then 8 for one int, because it has to align with VPTR. But if you put a char C in between, then 8 extra bytes are needed, because 4 for this, 4 for this, 8 for VPTR, and char requires another one. So then the alignment kicks in, and then you have 24 bytes. Now why I'm making all this here is because I want to talk about the dog object. Okay, and we inherit this publicly with the animal object. Right, so we have the animal object now. Now at this moment, if we take a look at the size of dog, let's see how much it is. Do you think it would be 1? Let's see. It is also 16 bytes. Why? Because it is containing the entire object of animal inside it. Alright, so that is why every derived object will contain this object of parent. For example, let's put another object, another element B. Okay, and we see this again. So we should have more, right? 16. Okay, this 4 and this 4 is now aligned. Let's put another stuff. Alignment is a tricky thing, very tricky. Let's see now. Okay, 24 now. So we create another class. We say German Shepherd, and we inherit from public dog. Okay, and we give it long and ID. Okay, and we need to, what happened? Oh, this is char, should be class long ID and semicolon, and we create the object shepherd of this. How long do you think it would be? It should be 32, right? Oh, why did that make a mistake? There you go, 32. So that's how the size and all work. So the point I was trying to make is that this class contains a VPTR. Children children contain entire parent chain objects when they are made here. When the object is created, they will contain the entire parent chain. Also, an empty class size 1 byte. So what else can we discuss? So we were talking about polymorphism, all right? So the idea is that a base class pointer is basically able to point to all the children or grandchildren or great grandchildren. The base class pointer can point and manipulate all the things. The question is that what is the use of this? The use of this is, you will see a lot in game programming when you have to drive menus and windows, or in game programming has a lot of use. In GUI programming, you will see this a lot when you have to do the similar stuff like games. You have menus and forms and other stuff with GUI contain, and buttons and whatnot. Okay. So another thing is that when we talk about object-oriented programming, there is something called solid principle. I will discuss solid principle in detail a lot. So S stands for single responsibility. Okay, what it says is that a class should be responsible for one thing and one thing only. O stands for open for extension and closed for modification. The class you should be able to extend, but nobody should be able to modify it. L stands for LISCO substitution. LISCO substitution says that wherever there is a parent class, it should be substitutable by the child class all the time. Then we have I. I we have forgot what it is. Now we have the dependency inversion. Okay. So dependency inversion says that higher level modules should not depend on the lower level modules or something like that. Lower or higher level modules should not depend on the other side. So I don't remember exactly the dependency inversion, and I do very well. So these are the code of object-oriented programming, and we will discuss solid in quite a bit of detail when we do the design part of C++, or rather object-oriented design. If you want to study more about design of software in C++, I can recommend the book C++ Large Scale Design or something like that by John Lacoste. It's a very fine book. Then we have pattern-oriented software architecture and all. You can read those books as well. So what I wanted to talk about was the polymorphism, and here we see that animal taking form of a dog. That is the crux of this. And we'll see real world users, how this works out, probably later. Okay. So I will end this video here, and I hope that you have found this video useful. So I thank you for watching the video, and I'll meet you again roughly after 4 days as C++, JavaScript, Python, and Rust video cycle. So ideally, ideally on the 4th day we will meet with another program on concepts of C++. So once again, thanks a lot for watching the video, and I'll take my leave. Have a nice day.